Hello, my name is Ben Monday, and I'm the president of Wildcat Rocketry, a junior in mechanical engineering, and a big Star Wars nerd. Today, you're watching as Kansas State University's Wildcat Rocketry takes you through our design and building of a rocket for the 2025 Argonia Cup. During this video, you will learn about our design overview, airframe, safety and staging electronics, propulsion, flight profile, and recovery systems. We hope you enjoy the show!
Okay. Hello, my name is Tanner Singletary, and I'm a junior in computer engineering, and I'm also the vice president of Wildcat Rocketry. I also enjoy doing competitive shooting sports. Our team started off the year by looking at the 2025 Argonia Cup mission and deciding the best path forward. This year involves building a two-stage L2 impulse rocket and carrying a payload of golf balls to the highest possible altitude. Rockets will be scored based on an equation of sustainer apogee, payload size, and total impulse. Based on the scoring equation and changes to the rules from last year, our team decided to prioritize a higher altitude with a smaller payload size as the optimal solution. This year, our rocket is going at nearly 7 miles into the air at supersonic speeds with a total impulse of about 4,600 newtons.
However it works,
To design and simulate this rocket, our team used SolidWorks, OpenRocket, and RasAero flight simulation software. With these tools, our team was able to easily train new members on quality software and design our rocket easily.
Hello, my name is Philip Shirkin, and I'm a junior in mechanical engineering and the secretary of Wildcat Rocketry. I enjoy playing the piano. Our rocket airframe stands 8 feet 5 inches tall, with a diameter of 2.1 inches. It weighs 6.4 pounds without motors, and 16.4 pounds with motors. Both the body and the nose cone are fiberglass. The fins are made of 8-inch carbon fiber attached with Proline 4500 epoxy. With such a small diameter rocket, our airframe had to have an innovative design with novel ideas. As a minimum diameter two-stage rocket, we had to take a unique approach to interstage construction compared to previous years. We decided to use an over-the-body coupler to connect our stages, which supports the electronics discussed later in this video.
Hello, my name is Adam Rickman, and I'm a junior in mechanical engineering, and I'm also the treasurer of Wildcat Rocketry. And something I do is I also do audio engineering for an a cappella group. Safely and routinely lighting the second stage is a critical challenge in two-stage flights. Our sustainer ignition system uses a unique ignition design based off the interstage layout. However, our electronic needs go further than just stage ignition. Our rocket contains a total of 4 flight computers split across the sustainer and booster. Our main flight computers are the Telemega in the sustainer and the Telemetrum in the booster. And both stages also contain an Easy Mini backup, all of which are designed by Altus Metro. We also have a featherweight GPS tracker in both stages. This is meant to supplement the GPS tracking on the main flight computers. However, we decided that we really needed this redundancy after a previous experience last year, where a nominal competition flight was, no longer nominal because we lost all tracking on the sustainer and never ended up finding it. So having that redundancy is going to be very important moving forward, especially as we're more than doubling altitude. Our staging logic is also much more advanced because of our prior experience doing two-stage rockets. Our team's first two-stage rocket for the 2023 competition was beset by a lot of sustainer ignition failures. Basically every single test flight had a different reason why the sustainer did not light, which has taken us several iterations to resolve. We are optimistic that our current iteration is our best iteration yet, as our previous rocket for the 2024 competition was able to consistently light the sustainer. However, it was never in a quite optimal way, so we were hoping that this year we were able to ignite the sustainer in the most optimal conditions possible.
Hello, my name is Logan Gamble, and I'm a senior in mechanical engineering, and I'm also this year's competition manager for the Argonia Cup for our team. A fun fact about myself is that I do astrophotography. This year, we wanted to properly select our motors to optimize our altitude as well as our overall score for the competition. Our rocket will use an Aerotech L1090W for the booster, and this motor was chosen to allow for a pretty fast descent off the pad and also give us the best chance to stay as straight as possible to light the sustainer and stay within the tilt angles that we need. We also chose to use all RMS hardware for our stages. This allowed us to more easily screw our motors into our minimum diameter rocket using a homemade aero pack retainer, minimum diameter aero pack retainer. In our sustainer, we will be flying a Aerotech K270W, and the K270 pairs really well with the L1090 due to its long burn, based off of our other two-stage flights, and just overall as a two-stage flight profile. We also used this motor combination last year and had great success with it, so we kind of know how it flies. Successfully lining our sustainer has been tricky in the past, but with some improved electronic and sustainer ignition systems, we hope to have reliable flights this year.
Hello, my name is Eric Kaufman, and I am a freshman in computer science. In my free time, I also enjoy astrophotography. The flight itself is probably the most exciting part of our year-long project, and this flight profile looks to be something special. With an initial thrust of 280 pounds of force off the pad, our rocket launches in textbook Wildcat fashion, fast. By the time our second stage ignites, the rocket will have already broken the sound barrier. At approximately 3 seconds after the launch, the booster will separate, and the telemega will check if it can ignite the sustainer motor. If the sustainer can safely ignite, the K270 will fire and carry the rocket to 36,000 feet at a maximum speed of Mach 1.6.
Hello, my name is Arthur Silver, and I'm a freshman in mechanical engineering. I speak French. Our rocket is designed with a total of 3 parachutes for safe recovery. The sustainer will have an 18-inch Rocketman drogue and 45-inch top flight main parachute. The booster, since it reaches far lower altitudes than the sustainer, will only have a 30-inch parabolic fruity chute for recovery. The stages are separated, parachutes are deployed using several black powder charges. The sustainer main chute is released using hand-end deployment, while the other 2 chutes drop normally. The booster's only chute deploys at booster apogee, gliding down to Earth at 17 feet per second. The sustainer drogue deploys at apogee, slowly the payload to 85 feet per second. The sustainer main deploys at 1,200 feet, safely returning the payload to the ground at 20 feet per second.
Our team is more excited than ever to compete in the 2025 Argonia Cup. However, before this video ends, it's only fitting that we thank the people who made this event possible.
Kansas State University, the K-State Salina campus, the College of Engineering, the Mechanical and Nuclear Engineering Department, the Department of Electrical and Computer Engineering provide faculties, funding, and equipment to help our team build rockets that we can be proud of.
Private sponsors like BHS Construction, GeoProbe Systems, Evelyn's Colossal Cookies, and Polymaker give us the resources to push the envelope and come back to the Argonia Cup better every year.
Our team would like to thank the Cloudbusters and Argonia Cup volunteers for hosting this competition. We'd also like to thank the people of Argonia, Kansas, and the students, faculty, and alumni of K-State who all have a role in making this competition what it is. A spectacular display of talent, resourcefulness, and community.
Thank you all for making the 2025 Argonia Cup possible. And as always, go Cats, and we'll see you at the rocket pasture.